Good morning everyone. So we'll go to the next video, that is next problem on beams, that is where you have a trapezoidal load given to you in the question. So as you can see, there is a trapezoidal load given to you in the question with a roller support at A point and with a hinge support at B point. So how to proceed with this problem? You already know how to convert UVL and UDL into point load. Correct. So the question is again the same question, that is find the support reactions for the given beam. Okay. So the first thing you will have to draw is, draw the FBD of this particular figure. So to draw the FBD, you have to draw the beam again. So I am drawing the beam A, B, and when you have a roller support, you have a single reaction RA, and when you have a hinge support, you have one vertical reaction and one horizontal reaction. These things you should be remembering. Okay, so at A I am marking RA, and at B I will be marking RB and HB. Now this load, how to mark it as point load on this particular FBD. This is the FBD for this particular figure. Okay, how to mark the load? So you already know how to convert UDL into, so this particular trapezoidal figure you can divide it into two. That is, if you divide a trapezoid into two, you have a triangle. This is a triangle and bottom is a rectangle. Rectangular load, you know, it is already a UDL, and triangular load is a UVL. So now you can see the height of this rectangle is 2 kilonewton meter. So obviously this height will be 2. So can you find the height of the triangle? That will be 8 is the total height minus 2. So you will get 6 kilonewton per meter. I hope that's clear. That's how you find the height of the triangle. Now you draw this particular rectangle down separately. This which is acting over an AB length, I am drawing it separately. This is the UDL which is acting over a length of 7 meter. And the value is 2 kilonewton per meter. Okay, now what to do here? How to convert this into point load, which is already something you are familiar with. So now draw the length again, mark it AB. See, this is 2 kilonewton acting per meter. How much meters is there here? 7 meter. So the total value of load will be 7 into 2, that is 14, and it will obviously act in the center because rectangular load is a symmetrical load. Means if you cut here from the center, it is same on both the sides. So obviously it will act in the center. That is, the value will be 7 into 2, that is 14 kilonewton. It will act in the center of 7 meter, that is 3.5 meter and 3.5 meter. So this is how you have converted this part of UDL into point load. Similarly, you have a UVL here which you need to convert into a point load again. So how many point loads will be there when you have trapezoidal load? You will have 2 point loads when you have trapezoidal load. One because of UDL, that is this one, and one because of the UVL. So now next thing I am going to do here is I'll be noting down this triangular load again here down. Okay, this is a triangular load that I have. Okay, and this height is 6 kilonewton per meter. Okay, and this is 7 meter. Now how to convert this into point load? You draw the beam again, AB. Okay, now see here, you know the point load value will be the area of the triangle. Now what is the area of triangle? Half into base into height. So here what is the base? 7. So half into 7 into height is 6. So into 6 will be the value of point load. And where it will act? Obviously in the centroid of the triangle. Now where is the centroid of the triangle? You should know that. So for that I will be drawing a figure here separately which shows the centroid of the triangle. So if you have a triangle like this, and suppose the centroid is here, this total length is suppose B and the height is suppose H. Okay, so this distance, that is this, when you're considering along this way, this is the apex and this is the bigger side. From the apex the distance will be 2 by 3 of the base and the remaining distance will be 1 by 3 of the base. Same way if you go up and down, okay, this is the bigger side and this is the apex. So what is apex? Actually apex is a pointed portion. These both will be apex. When you take along this way horizontal, this is apex. When you take along vertical, this is the apex. From the apex again we know it is 2 by 3 into the height H. Remaining will be 1 by 3 into H. So this thing you should remember, from where it is 2 by 3 and from where it is 1 by 3 of the given length. Okay, so here as you can see this is the apex, and when you go like this, so obviously that is required. So from this side 2 by 3, that means you can mark it here. The value is half into 7 into 6, right? And this is 2 by 3 into 7, just compare with the figure, and this is 1 by 3 into 7. So that's all the conversion of these into point loads. Now let's mark that into this FBD. So before that you should find out what is the value of 2 by 3 into 7 and what is 1 by 3 into 7. So that you can see here, 2 by 3 into 7 is 4.67, okay, is 4.67. And we know that at 3.5 we have 14 kilonewton load. First you mark that, then 3.5, this is 14 kilonewton load. Okay, suppose this is 3.5 meter, this is 14 kilonewton load. Remaining is also 3.5, but doesn't look, you can mark it in the center also, no issues. The next load you have at 4.67 as you have calculated, which is 2 by 3 of 7. So after some distance, suppose I am marking this is 4.67. This load will be, what is the value? 21. Okay, 21 kilonewton. Okay, so I hope it's clear. This this is the UBL and this is the UDL converted point load, and distances also I have marked here properly. Now as usual, after drawing this, you can do the analysis of the beam considering the beam is in equilibrium using the equilibrium conditions. Fx is 0, sigma Fi is 0, and moment about a point. Okay, once all these conversions are done, next step is you have to solve this beam by considering the beam is in equilibrium and using the equilibrium condition, that is Fx is 0, Fi is 0 and moment about A is 0. So if you write down the Fx, you can see only one horizontal force is there, that is HB. Okay, and so it will be obviously equal to 0. Now if you write Fy, you can see many vertical forces there. The sign convention is which is going up is positive and which is going down is negative. I'll show it here. Which is going up is positive, which is going down is negative. So as you can see here, RA is going up, so RA is positive. 14, RB is going up, so RB is positive. 14 is going down, so negative. 21 is going down, so negative, equal to 0. So you get the answer is RA plus RB is equal to 14 plus 21, that is 35. That you mark as equation number 1. So I hope that part is clear. Now next part is we have to find the moment of this particular beam. So for that, I hope this is okay. I'll keep it here and do. Okay, now to find the moment, the step is you have to take sigma ma is equal to 0. So first you have to write sigma ma, right? So as you can see here, the moment of RA to A will be 0 because it is passing through A. Any force when it is passing through the same point about which we are taking the moment will be obviously 0. Now next one is 14. If you take the moment with respect to A, the distance between 14 or perpendicular distance between 14 and A is this 3.5 meter. So obviously you'll have to do 14 into 3.5, and as you can see, you will consider the clockwise direction for moment. This you should remember, very important, that is all the clockwise is positive and all the anti-clockwise is negative. Okay, the convention for moment is taken as rotation clockwise or anti-clockwise, because moment as such means rotation. Okay, so 14 into 3.5. Similarly, if you take 21, that is also plus 21 into this total distance, that is between 21 and A, that is 4.67. Okay, see again, that is clockwise. Next one you have here is next is RB, but RB you can see it is not plus, so obviously no need to write plus, it is going anti-clockwise here, so it is, I'll write it below, minus RB into the total length of the beam, correct, that is 7 meter into 7. And what about HB? HB, even though it is not directly passing through A, its line of action is passing, or there is no perpendicular distance between A and HB. It's parallel actually to the point. So it can be neglected. So you get RB is equal to 0. So next step is you get 7 RB is equal to, remaining you need to calculate there. That is 14. I hope you can see, okay. 14 into 3.5 plus 21 into 4.67. Right. Okay. That is 147.07 divided by 7. So you get RB is equal to 21.01 kilonewton. So from equation number 1 we get RA is 35 minus 21.01, that is 35 minus answer, you get the answer is 13.99, or you can write 14 kilonewton. So you got the value of RA and RB like that. So whenever you have a trapezoidal load, you should remember to convert that into 2 point loads, that is UVL into point load and UDL into point load, because the trapezoidal load is made up of triangular load and rectangular load. So I hope all have understood this problem. One thing you should study here is about the support reactions. When you have fixed, how many reactions? When you have hinged, how many reactions? When you have simple and roller, how many reactions? So I hope it's clear, this part. To take the moment, you know the basic equation, that is moment is equal to force into perpendicular distance. Thank you.